A good morning from me, and a warm welcome to today's Tech Talk. My name is Stefan Maurus. I've been working for Bloom for almost 8 years now, and I'm currently employed in international sales. My job is to support several branches with regard to all sales-relevant topics. Further, I'm also a product expert for our probes with DIGILOG technology, the TC DIGILOG. And that's the topic of today's Tech Talk Online. In the following feature, you'll learn what a DIGILOG probe is and how it works. Using various application examples, I'll show you how it can be used and how you can increase productivity with the help of this technology. My goal in this video is to give you a brief overview of what our probes with DIGILOG technology are all about, how they work, and what information is generated for evaluation purposes. First, we'll take a look at the portfolio, followed by some application examples. What is DIGILOG? Let's start. DIGILOG. What does the term DIGILOG actually mean? What is meant by DIGILOG technology? We'll start off by taking a look at a normal probe. A normal probe usually works according to the digital principle. Digital means that the probe only knows two states, either it's deflected or it's not deflected. This is quite similar to a light switch. The light is either on or off. Our DIGILOG probes are also capable of working exactly to this digital principle, but not only. A DIGILOG probe is also able to work according to the analog principle. Analog means we not only recognize whether the probe is deflected or not, but also recognize how much the probe is deflected. So we actually monitor the degree of deflection. At the same time, we don't just generate a single signal during the measuring process, but instead we record a large number of measuring points during the entire measuring process. We're basically generating a data stream. A data stream in which thousands and thousands of measurement points are generated and can be used for evaluation. Later on, I'll use various application examples to show you what this actually makes possible. A DIGILOG probe combines the characteristics of digital measurement and analog measurement. How is this possible? How does a DIGILOG probe work? Let's take a look at the design of a Bloom probe. If we look at the inner workings of a Bloom probe, we find that the design of a Bloom probe differs slightly from most other probes on the market. Bloom probes are not equipped with a mechanical or electrical switch to generate the signal. Instead, our probes work with an integrated light barrier. Deflection of the measuring mechanism results in shading. This shading generates a voltage change. And this voltage change triggers the signal. This functional principle has the fundamental advantage that it is completely wear-free. This applies to all Bloom probes, regardless of whether they work with or without DIGILOG technology. It also offers a further and decisive advantage. In simple terms, this means that we can record the degree of deflection of the probe in the micrometer and submicrometer range. This enables us to evaluate a workpiece not only point by point, but we're now also able to scan a surface. And during the scanning process, we can record the deviation of the actual profile to the target profile. To understand this better, let's watch a short video. We see a component whose internal contour is to be monitored for dimensional accuracy. Now, we could record many individual measuring points to check the geometry. Instead, we place the probe ball on the profile and then trace the entire contour of the component. The travel distance of the probe is controlled by the CNC program. The contour is scanned, and we receive a holistic overview of the entire profile. The scanning process is not an absolute measurement, but a comparative measurement. Meaning that a master profile is generated once before monitoring a component. Master profile means that I record the profile of a good part. That is the master scan. This data is stored in the software. In mass production, all subsequent components are then scanned and the recorded profile is compared with the master scan data. We thus compare the actual situation with the desired target situation. We record whether the scan profile matches the specifications exactly or whether there are any deviations during the scan, in both directions, plus and minus. In order to monitor the component, the operator defines which limits should apply to the profile. In this case, the operator can distinguish between warning limits and tolerance limits. These limits are shown in the lower half of the screen. The warning limits can be recognized by the yellow color, the tolerance limits are displayed red. All limits can be freely defined. If one of these limits is reached or exceeded, a corresponding error is output and further machining of the component is stopped. In case the profile being monitored does not display the same tight tolerances across the entire range, the evaluation length can be divided into several segments. For these segments, varying wide or narrow tolerances can then be defined. Monitoring can also be stopped, if necessary, between the segments. Let's now watch the example video again to get a better understanding of things. This is a threaded rod on which the thread profile is to be monitored. Before the start of mass production, a master scan is generated once on a good part to record the target state of the profile. A feed rate of 200 mm per minute was selected for this specific case. You can see a relatively short stylus with a ceramic shaft and a very small ball. With regard to the stylus insert, there are no design restrictions in terms of material, length or probe ball. The design is optimally adapted to the respective measurement job. The master curve is recorded parallel to the scan. Software for evaluating the measurement data is integrated directly into the machine control. The results are visualized directly on the control screen. We also offer alternative solutions if, for example, full integration of our system into the machine control of older machines is not possible. During production, the components are scanned after the machining process, and the respective actual profile is compared with the data of the target profile. In the next video, we can see the simulation of an error on the component. A roughly 100 micrometers thick piece of adhesive tape simulates an error in the contour, which is detected during the comparison scan and leads to an error message. Before looking at a few more examples, let's take a look at the portfolio of our DIGILOG probes. Depending on the respective application, various probes are available. Basically, all DIGILOG probes are equipped with the proven shark measuring mechanism. Data is transmitted either by radio or cable. The devices with radio transmission are 100% compatible with our standard radio receiver RC66. This means that the DIGILOG probe can be combined as desired with other radio systems from Blum, be it a spindle or table-mounted probe, or even a surface roughness gauge or bore gauge. Up to 6 devices can be operated using one and the same radio receiver. At the beginning, I mentioned that the DIGILOG probes can also be operated like a normal probe in digital mode, i.e. switching mode. As with the standard probes, this is of course possible with a probing speed of up to 2 meters per minute and a repeat accuracy of 0.4 micrometers per minute. The speed for scanning a component depends on the respective measurement job. It is optimally adapted to the profile being monitored and the required measuring accuracy. Speeds of up to 5 meters per minute can be achieved. The resolution during a scanning process is 0.25 micrometers. And the data rate is 1 kHz. This means that 1,000 measuring points are recorded per second during the scanning process. The most common device is the TC64 DIGILOG. This device combines the measuring mechanism and the transmission unit in one housing. It's very compact. Data transmission takes place via radio. This device is mainly used on milling machines. An alternative is the TC63 DIGILOG, also a radio probe. It is a device with a modular design. The measuring mechanism is separate from the transmission unit in this case. Depending on the application, carbon extensions and elbow fittings can be used to adapt the probe optimally to the respective measurement job. The third device is the TC76 DIGILOG. This is only the housing with the measuring mechanism. The device is extremely compact. It measures just 25 mm in diameter. This device can either be combined with the modular device presented above, or it can be combined with a base featuring a cable connection for permanent installation in a machine tool. This version is used, for example, on grinding machines or robots. That was a lot of theory. I'd now like to go into a little more practical detail and show you a few examples where DIGILOG probes have been integrated into production processes. The first video shows a hardwired TC76 DIGILOG, which is permanently installed on a continuous generating gear grinding machine. Its task was to precisely record the position of the blank before machining in order to reduce the grinding allowance to a minimum. The lower grinding allowance in turn reduces the machining time. Using the DIGILOG probe, the tooth flank and tooth profile are recorded, much faster and more precisely than with any conventional measurement. The next application example also deals with gear wheel monitoring. A drive shaft is monitored on a turning milling machining center. The tooth flanks are checked for dimensional accuracy while the component is still in its original setup. The scanning process takes place at a speed of 1.8 meters per minute during the scan. A total of approximately 570,000 measured values are generated per drive shaft. Even adhering coolant does not negatively impact the measurement results. Our next example comes from the automotive industry. The valve seats on a cylinder head are to be monitored. Microbursts on the valve seat tools lead to faulty machining. Our DIGILOG technology provides a remedy. First, the probe is used in digital mode, i.e. switching mode, to perform various measurements. Then we change to analog mode to scan the three angles of the valve seat. The smallest irregularities caused by microbursts on the cutting edge are detected effortlessly. I also brought along an example from the aerospace sector. This involves the machining and monitoring of turbine blades, which presents manufacturers with major challenges. The profiles are extremely complex. Since this is the aerospace sector, the monitoring of components is of utmost importance. Reworking is difficult or even impossible. In this specific case, measuring the component took more than 24 hours. By using a DIGILOG probe, the component is no longer measured point by point. Instead, we scan the individual turbine blades. As a result, we receive a holistic overview of the entire turbine blade profile. One blade after the other is scanned. It takes less than 30 minutes to measure the component fully. In this case, our software is integrated directly into the machine control. The data is visualized directly on the control screen. The target curve of the master scan is displayed in the upper section and the actual profile is superimposed over this target curve. In the lower section, we can see the warning and tolerance limits. In this case, the deviation between the target profile and the actual profile is just 4 micrometers. And it's not only time we save when measuring, especially with this component, there's another particular advantage. Deviations between the target profile and the actual profile means that the component can possibly be reworked. However, if the component is measured in the measuring room, it is no longer possible to rework it, as it is no longer in the original setup. When using a DIGILOG probe, monitoring is carried out directly at the machine while the component is still in the original setup, which means that the component can possibly be reworked. This video shows another complex component. With our DIGILOG probes, we're not limited to 1 or 2-dimensional scans. Instead, we can use all the machine axes for the scanning process, like here on this 5-axis machine. In this case, our TC64D is used at quite an impressive scanning speed. But our DIGILOG probes are not only used on milling machines. They can also be used in turning machines to monitor workpieces. Here, we see the smallest device of the DIGILOG family, the TC76D. It is permanently installed and is used to monitor this slot. We're almost at the end of my talk. There are still numerous application examples I could tell you about. So let's summarize. DIGILOG is the combination of digital measurement technology and analog measurement technology. With an analog measurement, we don't just record a single signal but a data stream with thousands and thousands of measured values. This type of measurement allows the scanning of surfaces, and not just simple profiles, but also very complex ones. We compare the actual profile with the target profile and recognize whether the component is within the predefined warning and tolerance limits. All this leads to the following advantages. We can immediately detect whether any machining errors have occurred while the component is still clamped on the machine. No further scrapped parts are produced while the component is measured in the measuring room. The component can possibly be reworked, as it is still in its original setup. The scanning process considerably reduces the measuring time compared to conventional measurements. As you can see, there are so many advantages when using a DIGILOG probe. You could also summarize them in one sentence: increase your productivity, and that's exactly what we focus on. Blum-Novotest, focus on productivity. Thank you for watching. I hope you found it interesting. If you're interested or have any questions, our experts are always at your disposal. That's all for today. Take care.